for your outstanding introduction. All the credit goes to my students and postdoc everybody else. Being a growing world, the world requires a food system that are safe, nutritious, and sustainable. You all know that traditional thermal processing ensures safety, but gaps here is limited data is on thermal inactivation of microbes under very low relative humidity, and pathogen resistance increases significantly under dry conditions. So, main objective in this low moisture food is the measure the thermal resistance of salmonella and other microorganisms at greater than 120 degrees Celsius and relative humidity of 5 to 40%, 5% to 40%, using alternative desiccants for the precise humidity controls so that we can look at the thermal resistance of different microorganisms. The experimental approach we did, our students are doing is using the different desiccants and then measure the thermal resistance of some of the microbes at more than 120 degrees C and relative humidity 5 to 40%, using alternative desiccants for precise humidity control. Some of the results we got so far is on 2 different microorganisms. Strong depends on relative humidity. Small increases in relative humidity significantly reduce the D values. So molecular C3A achieve the driest condition for low moisture foods. So I'm going to show you some of the results we got for low humidity environment. The challenge here is measuring thermal inactivation of pathogens in low moisture levels at high temperatures and very low humidity also. So solution is, if you can employ advanced desiccants to control and maintain the precise low humidity environment in thermal analysis cells, that will be the key thing to do so that you can really do the analysis of thermal resistance, thermal inactivations. So out of all, we tried 3 different desiccants, Silica gel, molecular C3A, and activated alumina. Out of these 3, silica gel water activity decreased with the increase in moisture level. The temperature is 100 degrees Celsius. For molecular sieve, the consistently low activity, water activity, even at the higher moisture levels, we were able to achieve that. For activated alumina, decrease in water activity while raising the moisture content level. So from this, we also study the thermal resistance at 120 degrees Celsius with the raw desiccants. So you can see that from these results, the key findings are the activated alumina showed the less resistance reduction due to shortest D value, D value of 24 minutes compared to 26 minutes. And then molecular CA was the most effective desiccant, exhibiting the longest D value, and a higher pathogen resistance was associated with the relative humidity conditions. So low relative humidity conditions leads to high pathogen resistance. So these are some of the findings we were able to obtain, and some of the conclusions from these thermal technologies. Out of all 3 desiccants, molecular C3 was the most effective desiccant, and humidity is a critical control parameter. Even small increase in relative humidity significantly reduce the D values, and then thermal resistance salmonella is strongly RH dependent. So conditioned silica gel provides reliable relative humidity control. So overall impact is precise control of humidity is key in addition to temperature. Is essential for designing, validating, and optimizing thermal processes for the low moisture foods to ensure the microbial safety. So that's what I want to convey to you in terms of the thermal processing. What's new things happening in this area.